So this presentation is about actuator design with flux. And why we decided to talk about this one is because actuator design can be applied to many domains, in power industry, automotive, aerospace, robotics, and it concerns quite a lot of applications like circuit breakers, protection relays, electromagnets, voice coils, printer needles, things like that. And today we will look at a specific application with solenoid. When you design an actuator, what you can get with flux is quantities like induction or magnetic force. These are magnetic quantities, but also because we have the electric circuit coupling, we can have access to electrical quantities like the voltage, the current, or the inductance of the coil, for example. So here we get the typical curve of the current in a coil in tension when you close the air gap of a solenoid. And we have also the coupling with the mechanical equation, that is, we consider the movement of the mobile part, and then we have access to the position versus time. So we see here the actuator that is moving from the open position to the closed position, and to all the kinematic values like acceleration, speed, and we really get the full dynamic behavior versus time of the actuator. To broaden the view of all the tools we have for the design of such actuator, in fact we have not only flux, but we have also Portunus and Gotit. In flux, we will focus on magnetic analysis, and it's available for 2D and 3D exactly in the same environment. And what we may perform is magnetostatic analysis, transient magnetics, and in some cases for contactor application, for example, these ones work in AC, then we can consider also steady-state AC computations. Portunus, we will see here in this example, will be used to look at the full system and to have really the virtual prototype of the system, including the actuator. And it will be also a help in the early stage of the design for the pre-design. So we will see that in a moment. And Gotit. So we had this presentation from Philippe. It will really at each step of the design, it will help to do sensitivity analysis, optimization, to get the values of the design parameters from the requirements of the system. So in fact, the idea here is to take an example. We go through all these examples from the pre-design phase to verification phase. So we just imagine we are a solenoid designer, and we are part of a team that is designing a system in which there is this actuator. So we will go from the requirements that come from the system to the final verification. That is, we'll start with simple modeling in 2D magnetostatics and go up to 3D calculations. And we will use different tools we have, Portunus, Flux, and Gotit. So Gotit, we won't do really the demo, but we'll see some Portunus and Flux simulations. Well, so let's begin with the system. What is the system we intend to design, and what is the role of the actuator in this system? In fact, the actuator we try to design together is this actuator. So this is a full system and you have the actuator. So here you have a power circuit, and the role of this actuator is if I command this actuator and I put it in the on position, then it will close the contact and feed the power system. And I can turn it on or turn it off. And I have another role for this actuator, is that if here there is an overload that is detected by this sensor, then some information will be treated here, and then we'll ask the actuator to trip and open the contact. So if I have an overload on the line here, we will open the contact, and the actuator has this role in the system. So what I propose here now is to look at this system modeled in Portunus. Okay, so we have the full system here. In fact, we have the power line here with the switch that is commanded by the actuator, and the load of our circuit is very simple, it's just a lamp. And here also we have a very small resistance to simulate some kind of short circuit on the power circuit. Okay? And on the top of my model here, I have the electronic circuit that feeds my actuator, and with all the control. So here I have some advanced control, hysteresis control of the actuator. And then I have a first model of the actuator, and at this point I have just the main principle of the actuator. I don't really have the geometry. I just know that this actuator will be a simple one with a coil, with an air gap that will be closing, and then I have some magnetic circuit. So with this first model, I'm able to simulate the behavior of the actuator. So I will just run this model, and here I can control the power supply here. So you see here it's on, and then the actuator is closed. The actuator is closed, and my lamp here is red now. I can regulate the current. I can regulate the current here that feeds my actuator, so I can put it on or off here. And if a short circuit appears here, then the actuator will trip the switch here and it will open. Look at this. Okay, so now whatever happens, if I just want to open or close my contacts, it does nothing because I have detected a short circuit. Now if I do this, it comes back again. Okay, so now I have my full system, and I know what my actuator should do, and also I have all the requirements for my actuator, because I know now it should close in so much time, open in so much time, and so on. So we have the pre-designed phase here of this actuator directly in Portunus. So because we have this reluctant network model, also we'll be able to play with this model and determine first dimensions and also some analytical calculations for the coil characteristics, for example. Coil characteristics is not something that you have in Flux. This is something you have to calculate in an analytical way, and then Portunus is able to help you in this situation. So we'll have, in fact, the actuator will have to close or open in so much time, so in less than 30 milliseconds for the closure time, for example. And we'll have also to ensure some contact pressure when the power contacts are closed. the force on the power contact should be sufficient. So this is the kind of things we have as an entry point to the design. Then we will enter really the design phase, and we will do this job with Flux. And first we'll do some 2D axisymmetrical formulation and from a 2D sketching. So now we have decided a shape of the solenoid. So very classical, very simple shape for this example. And thanks to Flux, we will parameterize the air gap, the current in the coil. We can even do this kind of things using Gotit, that is taking the Flux model and then try to play on the input parameters to optimize the force, for example, in a specific position for a given power, or maybe to minimize the power to get a given force at a given position. So we won't do the optimization, we will just start with the 2D model, and the idea here is that I do a demo directly in Flux and see how fast we are able to get a first 2D model running. So my supervisor is open here, and then I will enter directly into the sketcher. And if I remember well, I will sketch my actuator here. So I know globally the dimensions. Okay, so just zoom at the good scale. Okay, so I need a 15 millimeter air gap. So I will start here at this point. Okay, and then I forgot to click somewhere. Okay, so let's put here a 50, let's choose a 50 here, and 5, no, something close to 7 for, okay, so I'm quite good here. No, this is 35, so no, let's do it a little bigger. Okay, like this, okay, I'm happy with this one. Then now I will draw the core. So the core is just starting here at 0, 0. And then I will choose a 5 millimeter here. No more 30 here. Voilà. It's 45. Okay. Let's do fast here. Okay, so you can see I'm guided throughout the process here. And okay, so I have my core. So maybe something I want to do is to get closer here. So just move this a little bit, because I think the air gap is too big here. So just we'll refine a little bit and put only 1 millimeter between the two. And then what I need more now is the coil. So I put the coil in the middle here, somewhere here. Okay, let's draw it. Okay, so looks good. Okay, so I have my actuator here. So it will be simulated in axisymmetrical model. So I'm finished here, but the only thing I want to do now is to parameterize the position. Parameterize the position of my mobile part here. So what I will use now is I will create a geometric parameter. I will call it air gap. So it's 15 millimeters, okay. And then I will edit all my points here, and I'll be able to parameterize all these 4 points with this away. So this is really the value of air gap, and this is air gap plus the size of the mobile. Okay, same here. And then I have air gap here. Okay, should be happy with this. Okay, so let's check if this is working well. Just edit this parametric jump. This parameter. Let's put 1 here and see what it goes, how it goes. Okay, I'm quite happy, so it moves as I want it to. Okay, so I'm already finished for this one, but what I need now is to create an infinite box where just go out of the sketcher. I will define directly my application just right now. It's axis symmetrical, and then I need to create this infinite box here to get the magnetic field correctly in the air. Okay, so here it is, and now it will be completed automatically. So now I have all what I need from the geometric point of view. And let's try then to go to the mesh, and let's try the one-click mesh, as I call it. Okay, this is it. Well, not too bad, but I'm not that happy with what happened here, because I know the air gap will close, and because it will close, then I have to refine the mesh in this area, and also maybe it's good if I refine here. So my choice here is to refine. Maybe I can change just a little bit also the relaxation factor here, and I will just change the mesh on this point, this point, this point, this point, and this point, and I will put a small size. And what is small size? Just have a look at it. The small value is, I will put something like 0.25. That will be the value I will use for the air gap when it is closed. So I apply here and mesh again. Okay, so looks quite good for me. I'm quite happy with this mesh. So maybe the good thing at this point is to save. Let's save it. Okay, and to get quicker to the results, I have prepared a Python file. And this Python file just defines the geometry, so the different regions. It will characterize, so you have the material also here that is used. It will define the characteristics of all the regions automatically. So I don't want to do that just in front of you. So what I do is I just select all my file here, and I will just run it. So here, when I click here, it runs all what I selected in the Python file. So just now close this window. So I see now I have a circuit. This is not what I wanted to do, so I'm dead here. Okay. I define a magnetotransition. I wanted to define magnetostatic physics, so I will close this one and reopen another one, which is magnetostatics. So my aim, in fact, now is to calculate some surface response. So I will, with my model is almost ready to solve now, and what I want to get is the flux in the coil and the force on the mobile path versus position and current, so position of the mobile part and current in the coil. And these tables, I will be able to use them in Portunus to represent the behavior of my device. So let's go and do it in the software. So I have my magnetostatic model. I also have some parameters like the force, the current. I have some sensors ready. So this is the flux and the force on the plunger. And then now I have just to solve, creating a new scenario. And because everything is parametric here, I will be able to select the air gap. So I will start with 0.25 with a higher limit of 15. And I don't want to do too many steps, so I will add a few steps only. 3, and then I refine at the beginning, and then let's put an 8 here, and then 10, 12, and 15. Okay. So I will have 10 computations for the air gap, and so I have to use the current. So the current is really controlling the current in the coil. And for the current, it goes from 1 ampere to 4 ampere, and let's put 4 steps. So 4 steps times 10 is 40 computation. Just apply it and just solve now. So it will take. So you see, I could solve using here the adaptive solver, which I won't do. And let's. Something nice happened. It just disappeared. Of course. What I didn't do is that I had to first to assign the regions, because I have defined all the regions, but I didn't tell what region was, what phase was affected to a region. So this is air. This is my plunger. This is my coil. And this is the core. Okay, so this time should be ready to solve also. Okay, so it will solve for the 40 steps. So it goes quite fast. After 4 steps, it takes a little bit more time, because then it remeshes, it changes the position. First, it changes the current, so it changes very fast. And then it changes the position, and at this point it has to remesh automatically all the geometry. Okay, so we are close to the end here of the calculation. And then we will have a look at, maybe just here to check. Okay, looks quite good. And now what I want to have is the curve, so the different curve versus air gap and current. So what I want is, I think is force. Or F4, okay. That is one, and then the flux. I just type it like this one. Okay. No, not on the same one. Just the force. So the force, yes. C'était pas F4. I don't know why. Okay. Okay. We have to move it here. So we have our curve here, and we can get exactly the same for the flux. Okay, so I have my curve here, and we can see also the effect of saturation with the current, and we have the effect of the network. Okay, so now I have my tables, and this table, what I will use them for is to verify that this design, if I put this design into the system, does it work as it was intended to work? And because it's importunus, then it's fast. So let's try this. So we have this model. We go back to Portunus. And when we compare this model to the model we had at the beginning, now the actuator is no more represented by a reluctant model, but we have a full model with the tables. So I have a subsheet here with the force table and the flux tables, the one that I just created, and it's now ready to run, and I can check if all of this runs correctly. So the lamp is hidden here, so just turn it on. So it takes a little bit more time to compute. The tables is something simple, but not as fast as a reluctant model. So we can check once again that if I short circuit, you see, when I will click on short circuit, then the green will just disappear, and just a little after the red on the lamp also will disappear. So hop, hop. You see, so the actuator really did its job, and we have all the curves here. We can check on the coil current, we can check the core position and the magnetic force, the spring force, and all this stuff. Okay. Then let's close this model. The limitation of this kind of calculation is that we don't consider eddy currents in the actuator. And it may happen in some cases if you have a high-speed actuator that you have eddy currents, and this is something we would like to check. And to do so, we have to go to magnetotransition analysis. Magnetotransition analysis will have the current variation directly in the coil within flux. We'll have the movement, and we'll be able to measure the effect of eddy currents. For example, here we have the curve of current. Here it is characteristic from the moment at which the actuator is closing. You see that it is closing a little bit later, and also if you look at the integral here, you can see that more energy is necessary to move the plunger. So the eddy currents we will take into account are really the eddy currents due to the current variations and to the movement, both. And everything will be calculated automatically. And what we have, and which can be interesting, is the adaptive time step, that we choose the time step in the software just to make the necessary calculation during the time. At this point, we also can use GOT-IT, and it can be used with a transient model. And at this point, then, we would minimize the response time of the actuator for a given power. So we have an example here where we have 15% of gain between the initial device and the optimized device for the response. But let's go back to flux, and we won't solve the transient model. I have solved it. I have prepared a a model already with everything solved, and then we'll be able to look at this model and see what we have. And maybe the first thing we can look at is a movie. The movie is interesting because we clearly see the effect of eddy currents here. So what you see here, if I go back to the first images, you see the flux here has not really penetrated in the bulk of the core or the plunger. So this is really due to the eddy currents that prevent the flux to go deep at first in the matter. So if when time goes by, then you see the flux that is going inside really the plunger, and also we have the movement and everything. So this is what we get, and what we get also is the kind of curves we could see. This is the current in the coil, and we also have the forces in the mechanical set. So this is an interesting curve in which we compare the resistive force. The resistive force is a spring. What we can see here is that the spring force is changing with the position. So this is something that was entered and that was defined thanks to a tabulated parameter. And this is usually the case for an actuator. It has to face some force that really depends on the position. And we see here the electromagnetic force. And in fact, the movement will begin just at this point. And because there is some inertia here, we see it goes, the force is stronger than the spring force, and can overcome easily the spring force here, getting up to 175, even close to 200 newtons. Okay? Then, going back to my presentation, up to now we had just the Portunus with reluctant model, with the tables. We could see in flux that eddy current can have an effect on the behavior of our plunger, of our solenoid. So now if I want to consider the full system with the eddy currents, I have to go into Portunus, and it is possible then to do co-simulation, and we have directly, now we replaced the table by a flux component into the system model. The kind of results we can have in yellow, we have the curve we obtain in Portunus with eddy currents, and the curve that we get in Portunus without eddy currents. So we clearly see here the effect, even at the system level, of the eddy currents. And then this one is to this curve just show you the difference between the three kinds of models: reluctant, table, and co-simulation model. And for the co-simulation, just for the sake of comparison, we cancelled the eddy currents, and considering all the materials being non-conductive. And what we see is that in this case, the tables and co-simulation give the same results. So it's what we expect. And we see for the reluctant model, then we have something quite different. So it's only for free design, right? But when you go from reluctant to co-simulation, then you need more time to solve. Now we are at the last step of the design, we go to the mechanical design, and because I'm just the electromagnetic designer, I won't take care that much about mechanical things, but when I go to see the CAD people, maybe this is what they will draw on their computer with Crowley or with Inventor or some other CAD editor. And then I have to check in Flux 3D that this design really corresponds to the requirements. So what I propose here is to do the job and just import the CAD model and bring the mesh to this model. So I'm now in 3D, and I will start a new project in which I will import the CAD model the mechanical guy just gave me, and mesh it automatically. Just wait for Flux 3D to start. So I think now I'm ready, and I will import. I have several formats of import, but what I have here is step file. I will select my step file. It is ready here. Click on OK, and then the software will import and do some healing operations automatically, some assembly operation automatically. And here I have the faces, I have some volumes available. And what I need before we go further is to define the air all around my geometry. So I propose to put same size as for the 2D. Okay. It's there, and making sure I have everything I need, I've completed automatically. That will build all the face volumes just all around my geometry. Okay. And now just go to the mesh, and I will just mesh the faces. So it may take some time, and why it takes some time is we will see it when we go deeper into the model. There were very, very small air gaps. Very small air gaps in the shape of the core. At this point, the software is trying to refine the mesh just in these little air gaps, and we'll see it does a great job in the end. And the nice thing is that I have nothing to do. I can talk with you. I can have coffee or tea. So that's nice. I hope I only have time for one tea, no more. Okay, this is finished. And by the way, I don't want to look at the infinite box that much, so I will just set it invisible so that we just focus on the device. I don't like to see the box. So you see here my mesh. Personally, I'm quite happy with this mesh because it's refined in the corners, in the rounds here, and also the little air gaps we have, they are somewhere here. Let me just zoom. So you see here, I have little spaces here, and then the mesh was very well adapted to this situation. So of course now I won't go through the whole process for 3D. In fact, this is exactly the same process that we could follow with the 2D. Of course, all the meshing or the solving time will be longer because this is 3D. But from the user point of view, the operations you have to do are exactly the same. then I will consider we are really at the end of the story. We could check in 3D our design from the real CAD model, and we could really go from the early design phase to this verification phase with the great features of Flux for this kind of design. We could see interesting features like Sketcher, the 3D import, the automatic mesh generation, the parametric analysis. You could see it was very intuitive and very straightforward to get this parametric analysis. The circuit coupling, the motion, of course, and Godit and Portulus that can really bring very interesting things during the design. Thank you.
Okay, so we're going to get a 10-minute break now. Thank you.